Okay, so we want to wrap up our discussion of nested quantifiers by talking about nested quantifiers. And nested quantifiers are essentially when we have more than one. Okay, so we could have a predicate that has more than one variable. We already talked about this. And remember, you could have two variables in a predicate, and they might even have different domains. Okay, and so if you're going to bind those variables, each one has to be bound by a different predicate, quantifier. Okay, and so when we have more than one quantifier, they're said to be nested. So for example, we might have this predicate right here, m, and notice it has two variables, x and y. That's right, and so the x and y would both need quantifiers to be bound. Okay, so this first variable, x, is bound by an existential. So this is bound by existential. Whereas this second variable, y, goes with this one. So this one is bound by a universal. Okay. So that means there's at least one x such that for all, and it could be separate domains, such that for all the y's in whatever the domain for y is, that m of xy is true. Okay, so that you'd only have to find one x and then have to convince, if this were true, you'd have to convince somebody that for that one x, no matter what y you chose from the second domain, it was always true. Okay, so here, again, we've got two variables in this quantified statement, but both of them are bound by existential quantifiers. Even if they're both the same quantifier, you still have to list them separately. So there's an existential quantifier for x, there's a separate existential quantifier for y. So each variable has to have its own quantifier. Down here, where we have three variables, I have this universal quantifier for x, I have this existential quantifier for y. If I don't list a quantifier for z, it's not quantified. So this is actually a free variable. It's not bound. Okay, so this wouldn't even be a proposition because we have a free variable in there. So if I want to bind z, I have to list a separate quantifier for z. Even if it's, even if it's a for all, even if it's, I just have to list a separate one. Okay. So that's all very abstract. Let's look at some specific examples that will make it a little bit easier for us to understand. So let's say we've got this example. So the predicate P of xy will be that x has written a program in y. The domain for x is people in this class. And then y is the set of languages Java, C++, and Python. Okay, so notice there's two different domains, one for x, one for y. And so if I look at this statement for all x, for all y, P of xy. So if you had to try to state that as an English sentence, like what is that trying to tell us? Matthew.
All students in the class have written programs in Java, C++, and Python.
Yeah. Okay, so all students in class have written programs, sorry, that's supposed to say programs, in each of the languages. Okay, I'm just going to say each of the languages. That implies Java, C++, Python, so I don't have to list them all out. Okay, so if I wanted to show that this was a true statement, okay, I'd have to go to every student and ask them, have you written a language, a program in all three of these languages? Have you written it? Okay, so that's how I could prove that it was true, but how could I prove that it was false? If I just find one student that hasn't written a program in all three of languages, then I know that it's not true. So is there anybody in here that has not written a program in Java and in C++ and in Python? All right, so we're just proving it's false. So okay, we'll do Evan. Okay, so this is false. Evan was the first one I saw, so our counterexample is Evan. Evan, what have you not written a program in?
Java.
Has not written in Java. Oh, you're lucky. All right. Maybe you can keep it that way. That would be great. All right. Then, the next one. There exists an x and there exists a y such that p of x, y. How do we translate that idea to English so that we can understand what it is? All right, Matthew's got these.
There exists a student who has written a program in either Java, C++, or Python.
Okay, good. So there's one student, there's at least one of them. There is a student that has written a program in at least one of Java, C++, or Python. Okay. One thing to look at when you're translating, going either direction, is sometimes there is a person or there's a student could be just translated as someone. Okay. So we could say someone has written a program in Java, C++, or Python. So that's just something to look out for as well. Okay, so if we wanted to prove that this one was true, what would we need to do? We just need to find one person that's written a program in one language. I bet we could find a person in here. Okay, let's see. Vaughn, what have you written a program in?
I've written a program in C++ and Java.
Okay, so we'll just do C++. So this is true. Okay, so we just need one example. So Ron has written in C++, for example. Okay. We could list his other language, but that's good. Okay. And then the next one, there exists a student, X, such that for every single language, P of X, Y. So what's that one saying?
There is a student who can program in Java, C++, and Python.
Good. So there is a student that has written in Java, C++, and Python. Who's written in all three? Anybody? All right, Victor is our example, so this is true. Victor has written in all three. So I'll give you an example there. Okay, and then the last one, for all x there exists a y such that P of x, y. What's that one saying? Go ahead.
All students have programmed in at least.
Good. All students have programmed in at least one of the languages. Okay. So, then, if I want to prove that it's false, I just have to find a student that hasn't written. If I want to prove that it's true, then I have to go to every single student and verify that each one of them. So, we should be able to do this pretty quickly. So, if you have written a program in one of these three languages, raise your hand. All hands are up. Okay. So, but notice that one was much harder for us to prove because I had to look at every single person and see that it was true for everyone, but I couldn't find a counterexample. So this is true. Okay. Everyone raised their hands. Okay. So, all right. So in general, we're trying to prove that these kinds of statements are true or false, we can view this as sort of this two-player game. So you've got the existential quantifier, and we've got a universal quantifier, and they're kind of playing a game, especially when you have one of each. So they can work together sometimes, but sometimes they're working against each other. Okay, so if we think about the existential quantifier, the thing that's easy to do is to try to prove it true. Because when I say there exists, I just need to give one example, and that's the easy way to prove it's true. That's the one that's easy. Proving existential false, that's the hard one, because you have to consider everything. Okay, so the existential is trying to just make the expression true because that's the easy thing to do. Okay. The universal quantifier, on the other hand, the easy thing to do is to try to prove that something's false. So that's what the universal is trying to do. Right? For the universal, if I can just find one counterexample, I can show it's false. So any variable that's bound by a universal, you're just trying to ask yourself, could I make this false? Could I make this false? And anything that's bound by an existential, you're saying, could I find a value that could make this true all the time? And so that's kind of the two-player game idea. So they're trying to, the variable associated with existential, you're just trying to prove something, trying to pick something to make it true. The universal, you're trying to pick something to make it false. Okay. So this is an example from like one of the textbook problems, like from the end of the chapter. Okay, so let's say we've got these and we're trying to determine if they're true or false. So let's think of it like this as this two-player game. So we look at x. X is bound by a universal. Okay, so what we want to be thinking about for x is, can I find the x to make it false? Okay. So remember, so that's what the universal, we're trying to make it false. So that's what the x is trying to do. Whereas the y is bound by an existential. So for y, we're saying, can I find a y to make it true? Okay. And there's this, here's this idea of this two-player game. Who's going to win? X making it false or y making it true? Okay, so this, since we're talking about the domain of all real numbers for both of them, is it true that for every single real number, every single one, I can find another number, okay, such that the product will always be positive? Okay, so if I'm trying to make it true, then I'm saying I can find a y that no matter what x you give me, I can make this true. Okay, so that's y's job, and x's job is no matter what y you give me, I can choose a value to make it false. So who's going to win, x or y? X is going to win. Okay, and what is x going to choose to make it false? 0. Okay, good. So if x is 0, okay, when I take 0, I don't care what y you give me, x times y, so if x is 0, then x times y is always 0 for all values of y. Okay, and so since the product is 0, is 0 greater than 0? No, it's equal to. Okay, so since, 0 is not greater than 0, this is false. Okay. So x just had to be clever and choose the right value to guarantee that no matter what y tried to do, it would win and it would be false. Okay. Let's look at the next one. Okay, now they're kind of changing roles. This time there's an existential with x, so this is trying to make it true. So this is, can I find an x to make it true? And y is being bound by a universal, that's trying to go false. So can I find a y to make false? So those are the questions that they're asking. Okay. So, here's going to win this time. So that the product of x, y, okay, can we guarantee that this will be false? Or could we make a choice to guarantee that that would be true? Yep, Matthew.
X equals 0.
X equals 0 again. X seems to be the winner. Okay. So once again, so if I find X equals 0, I don't care what Y is. When I say, once again, okay, X, Y has to be 0, so I guarantee this is always true. So that statement, X times Y equals 0, has to be true. Alright, so we get the idea. So here, X is trying to make it true or false?
False.
Trying to make it false because it's bound by a universal. So it's trying to ask, false, can I make it false? Y is trying to make it true, right? Can I make it true? Okay. So is there a number that I can pick to guarantee that this will be false, no matter what the other one is? Or is there a number, a Y, that I could pick to guarantee that that would be true, no matter what? This one's a little bit trickier. What is it, Evan?
Any negative number.
Any negative number. So let's just do something easy like -1, but yeah, you're right. So if I have a negative number, so notice what happens here. So, can I square a real number and get -1? No, I can square a complex number, an imaginary number, but I can't. So notice the domain is the set of real numbers. Okay, so there is no real number that can be squared and result in -1. Okay, and so I was able to choose an X value, make this false. So this is false. X wins again. Okay. This time, X and Y are actually kind of working together. So here, X is trying to make it true, and Y is also, they're not like competing against each other, but they're both trying to make it true, right? Can I just find an X value and a Y value? Let's coordinate our efforts. Okay, so that X squared equals Y squared and X and Y aren't the same thing. So can I find an X and a Y where their squares are the same, but they're not the same number? Yeah, Josh.
-2 and 2.
-2 and 2. So if I choose X is -2 and Y equals +2, okay, certainly their squares are equal and they are not themselves equal. So this one is true. Okay. And then the last one, so for all X and for all Y, is it true that X times Y is equal to Y times X? And so both of these are trying to find out, could I make this false? Could I make this false? Okay. So could I find a value to make it false? No, you can't, because this is an example of what law? The commutative property of multiplication, which we know is true for all real numbers. So there's no possible way, otherwise you would have disproved the commutative property of multiplication, and you can't do this, okay? This is always true by the commutative property of multiplication. Okay, so can I find a false? No. Can I find a false? No. Okay, this one has to be true. It's a law. Okay. All right. So just like we had De Morgan law for single quantifiers, you can also do it with nested quantifiers, and essentially it's kind of probably what you would expect. So imagine if I move it across this one quantifier, that universal turns into an existential, and when I move it against over the next one, that universal turns into existential. So I can just move it all at one time, and all of the quantifiers will switch. So when I move it past two universals, they both turn into existential. Notice when I moved it past here, the universal changed to existential, the existentials changed to universal. Okay, so you've got lots of options there, but it's going to change every single quantifier from one to the other that it moves past. Okay, so that's fairly straightforward. So that is forward. That's just for De Morgan. That should make sense. So let's practice doing it, using it. Okay, so let's say that I've got these nested quantifiers, and I want to write the negation of each of these statements, and then simplify it in a way so that the negation isn't in front of the quantifiers, but it's inside, and it only applies to predicates. So first of all, I'm going to start by writing the negation of the statement. So I'm going to put a not, and then whatever my statement was. So this is the negation of the statement. Okay. So I'm simply just rewriting that statement with a negation in front of it. Okay, so when it says write the negation of each, I'm just simply going to put a not in front of what was there. That's what makes it the negation. Okay, and now I want to make sure that I make it so that all negations immediately precede predicates. Well, this negation is not immediately before a predicate. So I've got to move it past the quantifiers. And so when I move it over here past the quantifiers and put it here, this quantifier is going to change to existential, and this quantifier, this existential, will change to universal. I know some of you can do this all in one. None of us get lost. Okay. So that is just applying De Morgan's law for the quantifiers. And now I can go and think about just my logical statement. So I've got a not in front of this logical statement, and now I can apply De Morgan's laws for logical operators to this one, this part of it. Okay. And so when I apply De Morgan to this part of it, okay, I've got a not the first one, I've got a not the second one, and that conjunction changes to a disjunction, right? And so now I've written it so that negations immediately precede predicates. So here I've got a predicate with a negation before it, a predicate with a negation before it, and every negation that appears is immediately before a predicate. Okay. Okay. So let's go on to the next one. We need to do the same thing. So let's write our negation first. So I'm just going to put a not in front of the whole thing. Okay. And of course, we'll just move it across the quantifiers, and so the existential will turn to universal, the universal will turn to existential, put the not on the other side. And then here's where it gets a little bit tricky. Okay, I only want negations immediately before predicates. Okay, and up here, I just moved the negation inside by using De Morgan's, but is there a De Morgan when we have implication? No, there isn't. So I can't just kind of move it. What am I going to have to do before I can apply De Morgan? Yeah, I'm going to have to use the implication law, so I have it written in a form that I can apply De Morgan to. Okay, so I'm just going to leave that there for a minute. And so the implication law tells me I should rewrite this how? You're like, how many rounds? You're going to give me all on the test. I don't need to know. Yeah. Nobody remembers. Okay, it's not P, Y, and then or QXY. Good. So not hypothesis or conclusion. Yes. And yes, I will give it to you, but I was, hoping that you've used it so much that maybe it was burned into your brain. Okay, so now that we've written it as an or instead of an implication, now we can use De Morgan's law. Okay, so it really was the same. So when I move the not in there, I've got to do not the first one, so that'll just turn into P of XY. Okay, the disjunction is going to turn to conjunction, and we've got a not the second one. And you will want to kind of remember this trick on Thursday. You won't have nested quantifiers, but there's a question on there where you're going to need to do this with just single quantifiers. So that little trick is handy. Yes?
So why did we move the negation to Q instead of P?
Why did we move it here? Yeah, so De Morgan says that if we have a negation outside, we have to not both of the things on the inside and then change the operator.
Okay.
Yeah, so I knotted the first one, knotted the second one, and then changed the disjunction to conjunction.
Gotcha. Thank you.
Yep, no problem. Okay. Now the last one is a little bit tricky here because I've got one set of quantifiers for this statement, okay, and so then I've got a separate set of quantifiers for this other one. So this is still, there are no free variables in here, okay, but here X is bound by a universal quantifier, here X is bound by an existential quantifier. So remember the way order of operations works, all of the quantifiers are done first, and then that logical operator is done last. So if you were going to parenthesize this, you would parenthesize it this way, okay. It's implied, they're not in there, but sometimes it's helpful to add your own parentheses in there so you can wrap your brain around what's actually happening. Okay, so imagine if I were going to negate this, okay, and I might even want to just switch to some square brackets or something in here because there's so many parentheses, but I had not, and then inside here I've got this first one with the existentials, oops, okay, and that's ended with the second one that has the universals. So I know there's a whole lot of parentheses, but I think that helps us kind of target how to do this. Okay. So the last operator that's being done here is the AND, right? And so the very first rule that I apply is going to be De Morgan for logical operators. That's the first operation that's going to be done. So I'm just going to do not the first thing, which is this one, and then change my conjunction to disjunction, and not the second thing. Okay. And now I can apply De Morgan's law for the quantifiers separately to this first one and separately to the second one. Okay, so I'm just going to move the quantifier past, and this is going to turn into for all x, for all y, not p of xy. This is just going to stay as an or. And then on this one, I would just treat this completely separately. I'm going to move this negation past the quantifier, so this turns into there exists an x, there exists a y, such that not q of xy. If you wanted to put little parentheses around these two little parts, you could. Okay. They're not necessary because we know order of operations, the quantifiers occur first and the logical operator last. Okay, but if it's helpful and you wanted to add parentheses in there, you could. Those are optional. But at least you want to parenthesize it in your brain so you can keep track of what's going on, even if you don't, write in your parentheses. Questions about that one, because that was tricky. Does that make sense to everybody? Is that good? Yeah. All right. Okay, and then the last two things in this section are some very specific cases of things that we want to be able to state using quantifiers but they're kind of tricky. So you kind of just have to know the patterns or memorize these patterns for them to work out. All right, and the first one is the everyone else. Okay, so if we have this predicate S of XY, so imagine there's like a group of people at a meeting or something, and S of XY means X shook Y's hand. So if I say for all X, for all Y, S of XY, okay, that means that everyone shook everyone's hand. Now the only way for that to be true is that every person in the room, okay, including me, has to shake everyone's hand in the room, including me, and I don't have to shake my own hand, right? And that's that's probably not the idea that you're wanting to get across. Probably it's more, common that I would want to be expressing the idea that everyone shook everyone else's hand. Okay, but I can't write it this way because that's not what it means. This is only true if everyone shakes their own hand as well as everyone else's hand. Okay, so the idea that we're trying to express is that for all pairs of people, as long as X and Y are not the same person, so that they don't have to shake their own hand, then X shooks Y's hand. Okay, so we're still talking about all pairs, so we want to universally bind X and Y. Okay, and then get this idea across, as long as X and Y are not the same. Okay, so I'm going to put my parentheses here so I make sure that everything's bound by these quantifiers. So I want to say that X and Y are not the same. So X is not equal to Y, and X shook Y's hand. Okay, so that's here, that's an S of XY. And then what should go in between here? So think about for universal quantifiers, sometimes we use implication, sometimes we use and, which is the one that we want to use when we have universal quantifiers. Implication. It's actually implication, yeah. Okay. Okay, so when we have existential, we use and. When we have universal, we use implies. Okay, so here we've got these universal, so that's a good clue that you should use implication in here. Okay, so as long as X and Y, X is not equal to Y is true, okay, then X shook Y's hand. Okay, so if they didn't shake hands, then you're going to have a true implies false. That'll be false. Okay, but as long as they're not true, you'll have true implies true. That's true. Now, for somebody that is themselves, where X and Y are the same thing, that will be false, and false implies anything is true. So even including people that are the same person, this will still be true for them. Okay, and they don't have to shake their own hand for this to be true. So that's the pattern that you should go after for everyone else. Okay. The other one that's tricky to represent is exactly one. Okay, so exactly one. So if you just use the existential quantifier, that means at least one, but it doesn't mean exactly one. If you want the idea of exactly one, that's a little bit trickier to do. So for example, let's say we have S of X would be X skipped class. So if I say there exists an X such that S of X, okay, that's true if one person skipped class, but it's also true if two people skipped class, or three people skipped class. I don't have to find one example, but there could be 8 people that skip class and it's still true. So if I want the idea that there is exactly one person and only one person skipped class, I can't just go with the existential quantifier. I have to doctor it up in some way to get the idea that it only happened for one and nobody else. So the idea that we're trying to get across here is there's a person that skipped class and all the other students didn't skip class. Okay, so definitely there exists a student X, okay, and that person skipped class. Oh yeah, sorry. Hopefully you're done with that previous one. So that person skipped class, okay, and all of the other students did not skip class. Okay, so inside here we're going to have all other students, and I don't want it to be the same variable. I need to have a new variable. So I'm going to say for all Y, okay, so if X is not equal to Y, and here this one is going with the universal quantifier, so we're going to use an implication here. So if they're not, then they did not skip class. Sorry, there's no X in there, just Y. There. I think that smashes it. There, yep. Yes.
Is at the end, is it not S of X? Is S of X just a skip class?
S of X skipped class, okay, but all other students that aren't X didn't skip class. We want to make sure that one's a Y.
So Y means all of them.
Yeah, so Y is all, so I'm going forward, they're in the same domain, so let's just say it's people in this class. So there exists some person in this class, and I'm going to call them X, okay? And then I'm going to go for all of the people in that same class, and Y isn't that person that I chose here. And that person, for all of those people, every single Y that isn't X, that person didn't skip class. Yeah. So we don't want to put X over there because then they would have to both skip class and not skip class, and they can't do that. Yeah, so these are all the Y's that aren't the same as that one. Okay. So again, like if you kind of know this pattern, understand this pattern, you can write it to do any kind of exactly one idea. Okay, so sorry for that mistake there. It's just a Y. Okay. I know, sometimes maybe you have to sit down and wrap your brain around that one, but yeah, these definitely can't be the same one as this one. So you need two and then we've got this, this quantifier is not outside the parentheses, it's got to be inside the parentheses as well. Okay, so there exists an X, that X skipped class, and for for all students in the class, as long as that student is not the same as this one that we found over here, that one did not skip class. Okay, X did skip class, Y did not skip class. And X and Y are two different people. All right, and then when you eventually get, I know you're not going to do this until after your test, but over the weekend when you get around to looking at the homework for this, you'll have practice ones, but it's good to see it before you have to do it in the homework because those ones are a little bit tricky. Okay, so the very end of chapter 1 is using all this logic that we've talked about to do logical arguments, and eventually this leads us to writing logical proofs. So that's where we're eventually going to get to. Okay, and so when we write a logical argument, we're going to have a set of statements that we believe to be true called hypotheses. And we want to make some kind of use valid logical reasoning to show that if all these hypotheses are true, then I can make this true conclusion. Okay. And the format of a logical argument would list all of these here. These are all called the hypotheses. Okay. Okay, and these are the things that we know to be true. Or at least we believe to be true. Okay. And then we're basically saying if all of these things are true, then I could make this true conclusion. So this thing down here is called the conclusion. Okay. And so we say that an argument is valid if I could take all of the hypotheses, put a conjunction, so I would have true and true and true and true and true and true and true. Okay. And the implication of that true implies, okay, now the only way for it to be valid if the conclusion was false, so we would have true implies false. That wouldn't be valid. Okay. I would have to have true implies true. So if it's a tautology, if it's always true, then I know it's a valid argument. But if it's false sometimes, well, then it's not a valid argument, right? So I can't make this conclusion from these hypotheses if that's false sometimes. Only if it's all the time true. Then these hypotheses will definitely always lead to this conclusion. Okay, so that is an example of a valid argument. Okay. So let's look at these and see if these are valid arguments. So here, these are all hypotheses. P implies Q. I know that's true. Okay. Okay, and P or Q, I would have to know that's true. So if I know those two things are true, could I conclude that Q is true? Okay, so we know that that's a valid argument if I could take the hypotheses and add them together. So if I take P implies Q, and AND that with P or Q. Okay, so this is the conjunction of the hypotheses. Okay, and I put that in an implication with the conclusion, and I check and see, is this a tautology? Okay, so if it is a tautology, I know it's a valid argument. If it's not a tautology, then I can't always conclude Q from those P's. Okay, so you can make your favorite kind of truth table. I think I'm going to do the shorthand one because this can end up being a lot of, so let's just put this under here. So I'm going to have true, true, false, false for P. And I'm going to have true, false, true, false for Q. I'm not going to copy them everywhere for Q. I'm just going to put the results under the operators here so that we don't have too much of a mess in here. Okay, so for our implication, we know the only time an implication is false is when I have a true hypothesis and a false conclusion. So this is the only false and the rest of them are true. If I go over here to P or Q, I'm just going to go look at these P's and Q's so I don't have to rewrite them. Okay, true or true, that's going to give me true. True or false, still as long as I have at least one, I'm true. False or true, I have at least one, I'm good. The only time it's false is when neither of them are true. And then this AND is going to look at these two right here and have to AND those together. So I have true and true, that's true. False and true, okay, they both have to be true. They're not both true, so this one's false. True and true, that one's true. True and false, they're not both, so this one's false. Okay. I'm going to go ahead and, I guess, repeat this one over here, just because I think it, okay. Maybe, but let me do a different color here. So now, here's my hypothesis of this implication right here. And here's the conclusion. So when I do this implication, I'm looking at the result, the logical result before is here in this column, the logical result after is over here. Okay, so I'm going to do true implies true, that's true. False implies false, that's true. True implies true, false implies false. Okay, so right here, the implication is a tautology. So this is a valid argument. So one of the other things that you can do if you don't want to go all the way to going and looking at the implication is you can just look at the conjunction of all the hypotheses, and you can look at the conclusion, and you know as long as when the hypothesis is true, the conclusion is true. Okay, so the other thing that you could go to do is look, and you can check. Okay, well here's my hypothesis. It's true here, and it's true here. Now when the hypothesis is false, anything goes. Like I could just throw those away. So I would just go look, and when this is true, I get a true. When this is true, I can get a true. So if you have a long table, really you only need to consider where the hypothesis is true. Does it match the conclusion? So that's the other way you can do these and kind of shorthand and skip a step. So you can also ask, what is the conclusion true everywhere the hypothesis is true? If the answer is yes, it's a valid argument. If the answer is no, it's not a valid argument. Okay, so sometimes that might be a little bit easier. Let me move this up. Okay. So maybe let's try that approach on this next one. So we've got two hypotheses. We've got P or Q, and we've got P. We've got to do the conjunction of the hypotheses. Okay. And then, so these are the hypotheses. And over here, we're going to look at not Q, and this is the conclusion. And so we just need to look, okay, so is everywhere that this one true, do we also have this one true? So let's go into our, so this is true, true, false, false. And this one is true, false, true, false. So our not Q is just negating these is going to be false, true, false, true. Okay, so when we OR them, as long as we have one true, the OR turns out true. So the first three are true, the last one is false. And then this AND is working on P, which happens to be in this column, and the result of this disjunction, which is in this column. Okay, so when we're doing an AND, those are the two things that we're ANDing together. All right, both of those are true, that one's true. Both of these are true, so that's true. These aren't both true. These aren't both true. And so now I can go back and just ask myself, okay, I just need to look at everywhere that the hypotheses are true. So that happens to be here and here. I don't care about the rest. If I have false hypotheses, anything goes. Okay. And now I check. Okay, do we get trues on both of those? Okay, yeah, there, but this one, okay, is not. So this is not a valid argument. Since the conclusion is not true everywhere the hypothesis is true. Well, the hypotheses are true. So that's a good way to like shorten your work and not have to go. Of course, if I went and put the implication in here, I would end up with false, true, 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 right? I know I'm going to get true whenever I have a false here. Really, I only have to consider the true implications. That's the only time you can get a false. So, but this one and the implication would give me a false, so it's not a tautology. It saves you from having an extra step in your table. Okay. All right. So here are some common arguments that people try to use as valid arguments, but they're invalid. So these are things that we want to recognize as, you know what, that's not logically valid. So that people try to do it all the time. Okay, so if we know that P implies Q, and Q is true, P must be true. So we might say something like, oh, you know, if a person studies for a test and they got a good grade, that person got a good grade, they must have studied for the test. Okay. Not always true, right? So it seems like logical or something, but it's not actually a valid argument. There's other ways, like some people don't even have to study and still get good grades. It's just not fair, but it happens sometimes. Okay, so there's other ways for it to happen besides P being true. So this is an invalid argument, and let's show that it is logically invalid. So once again, these are hypotheses. So if we did P implies Q, and we ANDed that with Q, that's our hypotheses. And then P, that's our conclusion. So here's our hypotheses, here's our conclusion. So let's do our true, true, false, false. Okay, I'm just going to go ahead and write them over here, so when we do our final comparison, it's easy to do that. And then our Q is going to be true, false, true, false. Okay, so the only time you have a false implication is a true hypothesis, false conclusion. That's the only false. The rest of them will be true. And then when I'm doing this AND, the Q is actually here, so I'm not going to rewrite it. And we're anding it with the result of the implication, which is right here. So those are the things that are going to get anded together. So when I and these, I get true, I get false, I get true, I get false. So once again, we can just look only at the places where I have true hypotheses and check. Do they match up with true conclusions? So here, yes, here, no. Okay. And so, since this one is not true, we don't always get a true conclusion. This is an invalid argument. Okay. So, this is called the error of the converse. Okay. So, let's say we know that P implies Q is true. What we're basically thinking is that, well, if Q is true, then P must also be true. Like if I turned it around, then the converse would also be true. So if Q is true, P would also have to be true. But we know that the converse is not logically equivalent to the original implication. Okay, so that's why it's called the error of the converse, because the assumption here, people using this kind of argument, they think that an implication and its converse are the same. They're not. Okay, so that is the error of the converse. Okay, this next one, where we've got P implies Q and not P. Okay, and then not Q over here. I've already got P implies Q, and just write those down. True, false, true, true. Not P over here is going to be false, false, true, true. Okay, not Q over here is false, true, false, true. Alright, so when I add these two, okay, these aren't both, so this one's false, but these two are true. So once again, if I go look at where the hypothesis is true and match those up, once again, we see there's a situation here where I have a false conclusion. So this is also invalid. Okay. And if you look at this one, we have, well, P implies Q, not P. Well, then it must be true that not Q. So if you think about it, not P implies not Q, that's the inverse. Okay, so that's what we're trying, so this one is called the error of the inverse. So people try to use this argument if they know P implies Q, if not P is true, they think certainly not Q must be true. It's not the way, the inverse is not logically equivalent to the original statement. Right, so that is an invalid argument, yes?
So a valid argument is only a tautology?
A valid argument is only a tautology. It has to be true all the time or it's not true. Like just because you found one example doesn't mean it's true all the time. So an argument means this always works no matter what the situation is. Yeah, so that's a valid argument. It has to work all the time no matter what, not just in one particular situation. Yes. Okay. Good. Okay. So we've got those, so let's say we've got some arguments that are written in English, okay, and we want to know if they're valid arguments or not. So, it's really hard to work with these big, bulky statements that are written out in English. It's much easier if we translate everything into, variables and symbols, and then it makes everything very concise. Okay, so let's say that the patient has high blood pressure or diabetes. Okay, so if we were going to translate this into a statement, the patient has high blood pressure, maybe we could call that like H, diabetes, maybe we could call that D. And since we have the or both in there, this would be H or D. Okay, the patient has diabetes, well that diabetes shows up again, this is D. And here we have a new thing, cholesterol. Well, maybe I should put B for blood pressure here. Let me change it to B. Because that also has the word high in it. So let's make this one C for cholesterol. Okay. So this is diabetes or cholesterol. Okay. Therefore, patient has high blood pressure, so this part would be B, or high cholesterol, this part would be C. Okay. So if we rewrite it in its symbolic notation, now we have this condensed version that represents the original problem, but it's much easier to think about because it's abbreviated. Okay, and so if we're trying to look at, okay, is this a valid argument or not, we simply just have to go and look at our truth table. So I've got, this one's really long though, isn't it? We've got 3 variables, a B and a D and a C. So I'm going to put it over here. So we've got B or D, and we want to AND that with D or C. Those are hypotheses, and over here we're going to want to look at B or C. Okay. So we've got 3 variables. How many rows am I going to need? We're going to need 8. Okay, so this one is long. So let's have B, that can be we'll do 4 truths and 4 falses. I might need some lines. Okay. 1, 2, 3, 4. 5, 6, 7, 8. Okay. So under B, I'm going to have 4 truths and then 4 falses. Okay, I'm not going to repeat it over here for this B. We'll just use the one we had over here. Maybe D, that can alternate by 2, so we'll do 2 truths and 2 falses alternating. And then our third variable is C, that'll alternate by 1. So this will be true, false, true, false, true, false, true, false. Okay, so B or D. So as long as we have 1 true that's going to be true, we just really need to look for 2 falses. So that only happens down here. So these 2 at the bottom are false. Everything else has at least 1 true. All of those are true. D or C. So here's the D. Here's C. Again, that's only going to be false if I have 2 falses. So that happens here on the 4th row, and it happens here at the bottom. Okay. But all the rest of those have at least 1 true. Okay. So here's the result of this disjunction. Here's the result of this disjunction. And so here, the conjunction, we have to use those 2 rows. Okay, so as long as they're both true, we have true. Those are both true. Those are both true. Those are both true. Nope. Those are both true. Next ones are both true. Nope. And nope. Okay. And over here, conclusions, B or C. Okay, so that we're looking, here's B, and here's C. As long as one of those is true, okay, we've got a true. So let's just look for 2 falses. So here, and that, what's that, the 6th row? That one's false. And then here in the last row, that one's false. That's the only place that we have both of those is false, so everything else should be true. And now we just have to look, alright, only when our hypotheses are true, so there's 6 of those options. Okay, so we get a true there, that one's good. We get a true there, that one's good. We get a true there, that one's good. So far so good, and then we find one that's not. Okay. So we do not get a true conclusion for every single true hypothesis, so this one is invalid. Okay, I think we have just enough time to finish up these last 2 because they're a little bit easier. Okay. We'll do this one next. So, alright, he studied for the test, or he failed the test, or both. So let's do studied as S. Failed will be F, so that's S or F. Okay, he passed the test, So that would be, well, not failing is the same as passing, so we can reuse that one. And so can we conclude that he studied for the test? Alright, so this one only has two variables, that's good. So we have S or F. We have to end that with not F. And we have to compare that with the conclusion of S. So two variables, we only need to do true, true, false, false. F is going to be true, false, true, false. I'll go ahead and write the not F so we don't have to try to do that in our brains. Okay, when we order the two, all these trues only have at least one true, so those are the first three. The only one that doesn't have at least one is on the bottom. So that and is going to apply to the result of the or and the negation of F. Okay, so that's only true. Okay, is it true here? Okay, no, that one's false. This one's true. This one's false. This one is false. I'm just going to go ahead and repeat the S over here so we can look at it. Okay. So we only need to consider true hypotheses, which happens exactly once. Do we get a true conclusion? Yes, we do. So this one is a valid argument. And the last one, I'll let you go. Okay. If the square root of 2 is irrational, then 2 square root of 2 is irrational. 2 square root of 2 is irrational, therefore the square root of 2 must be irrational. Okay, is this a valid argument? Alright, so let's have this one be, this one about the square root of 2 is going to be P, and this one about 2 square root of 2 is going to be Q. Okay, so this one right here is Q, and this one right here is P. So if we were going to write this out, we would have P implies Q, Q, therefore P. Have we seen this before? Like for instance, have we seen it today? Yes. So I don't need to go through all of this again, right? I can recognize, wait a minute. I know this is a well-known error. This is the error of the converse, right? There it is. P implies Q, Q, therefore P. Okay. So this is not a valid argument. This is invalid. This is an example of the error of the converse. Okay. So one thing that we notice here is that when you recognize a bad argument, you don't have to go through lots of work, okay, to recreate it. You recognize the pattern. And that's what we'll look at next time. Also, like if you didn't feel today like, oh my goodness, truth tables are really tedious. I mean, I hope you felt that way a little bit, because next time we're going to talk about doing rules of inference, where you can just do proofs by recognizing the arguments, and you don't have to do truth tables, and they're so nice. Yes?
Is there a special name that other really common invalid argument?
That is the error of this one is the error of the converse, this was the error of the inverse. Yes. Yes.
Stay here.